Imagine a solid so light it's barely denser than air, or maybe a liquid that literally climbs up walls against gravity. What if I told you there's a black so dark it makes 3D objects look completely flat? Today, you and I are going on an adventure into the truly bizarre and frankly brilliant world of materials science. Welcome to the deep dive, where we unravel complex topics and find those fascinating nuggets of knowledge. You've asked us to explore the top 5 weirdest materials known to science, and let me tell you, this list, it's going to challenge pretty much everything you think you know about matter.
Absolutely. Our mission for this deep dive is really to unpack these, mind-bending substances. We'll explore their unusual properties, dig into how scientists discover them, and crucially, look at the revolutionary ways they could impact our future. Or, in some cases, how they already are. Get ready for some genuine aha moments and some surprising facts that will truly stretch your understanding of what matter could even be.
Okay, let's jump right in. Kicking off our countdown of the weirdest materials is something often called frozen smoke, but it's actually a solid, aerogels. When you see it, it looks like this ghostly blue cloud, hence the nickname. It's barely denser than air, yet it's rigid. It's solid. And get this, it holds the world record for the lightest solid and boasts an astonishing 15 Guinness World Records. It's genuinely unlike anything you've ever touched, but how? I mean, how do you even create something so incredibly light, almost fragile looking, yet rigid?
Yeah, that's where the real genius comes in. The first silica aerogels were reported by Samuel Kistler way back in 1931. His ingenious process involved carefully replacing the liquid within a gel with gas. All while, and this is the tricky part, meticulously preserving its delicate, solid network. Think of it like taking, say, a Jell-O mold and somehow magically extracting all the water and replacing it with air without the whole thing just collapsing. That delicate, porous structure is precisely what gives aerogel its incredible, almost contradictory properties.
And what incredible properties. I mean, it's an insulator beyond belief, provides 3 times more insulation than the best fiberglass, and it can withstand temperatures of, 3,000 degrees Fahrenheit? Just incredible. NASA naturally put this to amazing use, like on their Stardust mission, right? They used aerogel to gently catch high-speed comet particles.
Exactly, and interstellar dust, slowing them down without causing any damage. It acts like a super gentle brake.
Wow. And it kept the Mars Pathfinder rover warm during those freezing Martian nights, too, literally insulating a robot on another planet. But, okay, with something that sounds so delicate, I can't imagine it was easy to get it out of the lab and into, actual products, right?
Wow. You're absolutely right. Yeah, traditionally, aerogels were hard to handle, very costly to make. That was a huge barrier for, widespread commercial use. But here's where collaboration really made the difference. A small business, Aspen Aerogels Inc., it was actually spun off from Aspen Systems Inc., partnered with NASA. This was through a Small Business Innovation Research, or SBIR, contract with Kennedy Space Center. And this collaboration, featuring James Fesmeyer, who's a senior principal investigator there at Kennedy's Cryogenics Test Lab, led to revolutionary manufacturing methods. They figured out how to make robust, flexible forms that drastically cut production time and costs, made it actually viable for industry.
That's fantastic. A perfect example of space-age tech coming right back down to Earth and solving problems. So this partnership basically transformed aerogel from a fragile lab curiosity into practical stuff, like flexible blankets. We're talking cryogel, space loft, pyrogel, now used in industries from oil and gas to aerospace. You could insulate an entire polycarbonate plant with this stuff, or, get this, providing insoles for Mount Everest climbers and ultramarathoners.
Right, because they prize the material for its super lightweight and extreme insulation. It really shows how far a dedicated team can push materials' potential when they work together.
Okay, shifting gears. From the ethereal to the utterly opaque, let's talk about our next material, Vantablack. This isn't just a very dark color. It's a material so dark that it absorbs an astonishing 99.965% of visible light. When you coat an object in Vantablack, it literally loses all visible detail. Your eye just can't perceive edges or contours. It makes 3D objects look completely flat, like a black hole has opened up on their surface. It's really eerie. But how do you make something that basically eats light?
Yeah, the science is pretty remarkable. This super black coating was pioneered by a company called Surrey Nanosystems, a spin-out from the University of Surrey. They first released it in 2014. It actually grew out of earlier work at the UK's National Physical Laboratory before the whole Vantablack trademarked family emerged. And the trick isn't a pigment like paint. It's a microscopic forest of carbon nanotubes, vertically aligned nanotubes specifically. When light hits this forest, it gets trapped between the tubes, bouncing around until it's almost completely absorbed rather than reflected back to your eye.
So your brain just gets no information back.
Pretty much. That's why you can't process any shape or detail. It's just gone.
So if it's literally sucking up light, what kind of problems does this solve? Where do you use something like that?
Well, its main use is in suppressing stray light in incredibly sensitive optical instruments. Think satellites, telescopes, places where even the tiniest bit of scattered light can totally mess up critical data. By coating internal components with Vantablack, they ensure these instruments get the cleanest possible view across the UV to the infrared spectrum. What's intriguing now is that newer variants are being tailored for advanced driver assistance systems, ADS sensors in cars.
Oh, interesting. For self-driving cars.
Exactly. This could significantly improve optical stability, making their eyes on the road much more effective, especially in tricky lighting conditions.
Huh. So while it might not be the next hot car paint color, though that would look kind of cool, its impact in these high-tech areas, especially for the future of autonomous driving, is potentially huge. All right, now for something completely different, something you might have actually played with as a kid, though you probably didn't know the deep science behind it. Oobleck. The simple mix of cornstarch and water, it just completely defies expectations. Handle it gently, it flows like a liquid. But apply sudden force punch it, squeeze it, try to run across a pool of it, and bam! It instantly stiffens, acts like a solid. I definitely remember making this as a kid. Never realized I was dabbling in advanced physics. It's famously named after that gooey green stuff from the Dr. Seuss book, right? Bartholomew and the Oobleck. How does this simple mixture do something so bizarre?
It really begs the question, doesn't it? What we have here is a classic example of a non-Newtonian fluid, specifically a shear thickening one. That just means its viscosity, its thickness or resistance to flow changes depending on the force or shear applied to it. When you apply a fast, sudden shear force like a punch, the cornstarch particles basically jam together. They trap the water between them and briefly act like a solid structure.
Ah, okay.
But if you ease up or apply a slow, gentle shear, the particles can slide past each other again and it flows like a liquid. It's a fantastic hands-on way for literally anyone to experience these fundamental physics principles.
It truly is. And that's why it's primarily used in education and public demos, right? It's such a great, tangible way to teach complex rheology, which is the study of how stuff flows into forms. You see it in those cool standing wave demonstrations on speakers or, yeah, those viral videos of people actually running across pools of it without sinking, as long as they keep moving fast.
Exactly. It's physics you can feel right in your kitchen. Super accessible, super fun.
Okay, up next, prepare to have your mind truly bent. We're talking about a liquid that literally climbs walls. Superfluid helium. Below a critical, incredibly cold temperature, we're talking just a couple of degrees above absolute zero, liquid helium transforms. It becomes a superfluid. And that means it has effectively zero viscosity, zero friction, so it flows without any loss of kinetic energy, like endlessly. And it forms this thin film, the Rollin film, that creeps up and over container walls, completely defying gravity. It's wild.
It really is something else. The discovery of superfluidity in helium-4 was made independently by Piotr Kapitsa and also by John F. Allen and Don Meisner back in 1937. Though, interestingly, there's some thought that high-chemical ions might have actually observed this phase transition even earlier, in 1911, the very same day he discovered superconductivity. Yeah. And later, the brilliant Soviet physicist Lev Landau developed the two-fluid quantum theory to explain its, well, mind-bending behavior. What's truly remarkable is that the discovery of superfluidity in helium-3, a different isotope, was even the basis for the Nobel Prize in Physics in 1996. So it's a huge deal in physics.
It's just mind-boggling. Flowing without resistance. This isn't just weird. It's where the bizarre rules of quantum mechanics, usually stuck in the tiny world of atoms, start playing out on a scale large enough for us to actually see. It can flow through ultrafine capillaries with virtually no resistance, right? And sustain that flow for ages without slowing down.
It's a macroscopic quantum effect. Truly strange.
And didn't scientists observe tiny whirlpools in it, like perfect little vortices?
Yes, quantum vortices. Another signature of this quantum behavior. Wolfgang Ketterl and his team at MIT experimentally proved superfluidity in an ultra-cold fermionic gas that was lithium-6 back in 2005 by observing these vortices.
And wasn't there that experiment where they slowed down light?
Yes. Lin Hao. She famously created a condensate of sodium atoms in 1999 to slow and even completely stop light pulses. Different system, but related to these extreme states of matter.
So what are the applications for something that climbs walls and flows forever?
Well, it's not exactly a party trick. It's absolute crucial groundwork for everything we do in low-temperature physics and ultra-precise experiments. For instance, in some experimental designs, like one called the D-Light experiment, Scientists actually have to include things called film burners.
Film burners.
Yeah, just to stop this creeping superfluid film from reaching their sensitive detectors. It highlights the extreme control needed when you're dealing with it. It also has potential practical uses, maybe like dissolving substances in a unique quantum solvent.
Hmm.
So while you won't encounter this on your morning commute, it reveals deep secrets about quantum mechanics and enables incredibly sensitive science. Pushes the boundaries.
Okay, finally, we arrive at a material that's been dubbed the holy grail of physics, though it's also steeped in some pretty serious scientific debate. Metallic hydrogen. For nearly a century, scientists have theorized that under absolutely immense pressure, hydrogen, normally a gas could transform into a metal. And not just any metal, one predicted to be a room temperature superconductor and potentially metastable, which means it could stay metallic even after you release that incredible pressure. Imagine the implications of that.
Yeah, the quest for metallic hydrogen goes way back. Wigner and Huntington first theorized its existence in 1935. Then, fast forward to 2017, Harvard scientists, Isaac Silvera, he's the Thomas D. Cabot Professor of the Natural Sciences there, and a postdoctoral fellow, Ranga Dias, reported something huge. They published in the journal Science that they had successfully created metallic hydrogen at an astonishing 495 gigapascals. GPa.
How much pressure is that really?
To give you a sense, it's more than 71.7 million pounds per square inch. That's pressure greater than at the center of the Earth.
Right.
However, the claim immediately drew a lot of scrutiny. It remains pretty controversial in the scientific community. It really needs unambiguous, reproducible synthesis. This whole ongoing debate isn't just about a material. It's a living lesson in how science works, right? How breakthroughs, especially at the absolute edge of our capabilities, are rigorously checked for reproducibility. That's the cornerstone.
That's a huge asterisk then on something potentially so groundbreaking. But okay, let's say if this holy grail is ever reliably proven and made metastable, the applications are just world-changing. First, energy. A room temperature superconductor. That could revolutionize power transmission. Think about it. Something like 15% of energy is lost just sending it down wires today.
Right, dissipated as heat due to resistance.
Wires made from metallic hydrogen could eliminate that loss. It could also enable magnetic levitation for super high-speed trains, make electric cars way more efficient, improve all our electronic devices.
And superconducting coils could store huge amounts of excess energy with zero resistance, solving massive energy storage challenges.
And space travel.
Oh, the potential there is just as monumental. If metallic hydrogen is indeed metastable, it would hold all that tremendous energy used to create it. If you could convert it back to molecular hydrogen, it would release that energy, making it the most powerful rocket propellant known to man. By far. It's theorized to have a specific impulse that's like rocket fuel efficiency of 1,700 seconds. Compare that to just 450 seconds for today's best chemical fuel.
Wow. That changes everything for space exploration.
It could easily allow us to explore the outer planets, maybe single-stage rockets to orbit, larger payloads. A truly monumental leap.
Okay, but the challenges for actually using this stuff seem immense, beyond the whole debate over whether it's been made reliably.
Absolutely. The conditions required are just extreme, that nearly 500 GPI of pressure, the tremendous energy needed to achieve that. Silvera and Dias in their experiments used specially treated synthetic diamonds in something called a diamond anvil cell to squeeze the hydrogen. They even noted that diamonds themselves can weaken and break under such pressure. They had to use a reactive ion etching process and an alumina coating to prevent the diamonds from becoming brittle and failing.
So it's not just hard to create, it's pushing the limits of what our tools can even withstand.
Exactly. But if it can be reliably created and made stable, it would fundamentally change our world. Power, transport, exploration, everything.
So as we wrap up this deep dive into the truly bizarre, let's pull out some key takeaways from these mind-bending materials. First, I guess they really show us that our everyday experience of solid, liquid, gas, it's just a tiny slice of what's possible, right? The rules can totally change under extreme conditions.
That's a great point. And connecting that to the bigger picture, science really thrives on these extremes, doesn't it? And often through collaboration, like we saw with NASA and Aspen aerogels. From the intense pressures for metallic hydrogen to the cryogenic temperatures for superfluids, breakthroughs often happen right at the edge of what we thought was possible. But these discoveries also hammer home the vital importance of rigorous testing, scrutiny, reproducibility. That's how we build reliable knowledge.
And finally, what seems weird today could genuinely be world-changing tomorrow. The seemingly strange properties of these materials, aerogel's lightness, Vantablack's darkness, superfluidity, maybe even metallic hydrogen, They aren't just curiosities. They hold the potential to revolutionize energy, transportation, space exploration, even how we teach science to the next generation.
Absolutely. The universe is constantly challenging our assumptions. It reveals a cosmos where the ordinary can become utterly extraordinary just by changing the conditions. It's a powerful reminder that our understanding is always, always evolving.
So, as we wrap up this deep dive, here's something to think about. What other mind-bending materials might still be out there just waiting to be discovered? Materials that could change our world in ways we can't even begin to imagine right now.